My name is AJ Boydston. I'm an assistant professor here at the University of Washington. So it's a great pleasure to welcome all of you to our campus. I'm also one of the local co-chairs and wanted to say that it's been a real pleasure working with Scott in having even just a small part in hosting what has been such a great symposium so far. And tonight's doubleheader, I think, will certainly continue that trend. The first speaker I have the pleasure of introducing is Professor Larry Scott, who comes to us from Boston College. Professor Scott received his bachelor's degree with honors in chemistry in 1966 from Princeton University, where he did research with Professor Maitland Jones, Jr. He then went to Harvard University to do his PhD in chemistry with Professor R.B. Woodward. After finishing his PhD in just 4 years, he went directly into an assistant professorship at UCLA, and in 1975, moved to the University of Nevada in Reno, where he was promoted to full professor in 1980 and to foundation professor in 1985. He also served as the department chairman at UNR from 1988 to 1991, and I believe in 1988 also had a visiting professorship at Harvard University. So good to stay busy, I suppose. While at the University of Nevada, he received awards for excellence both in teaching as well as in research, including special commendation from the university's Board of Regents. In 1993, he moved to Boston College, where he is currently the Lewis and Jim Vanderslice and Family Chair in Chemistry. Professor Scott has served the scientific community in many ways, and in particular as the chairman for the Gordon Research Conference on Physical Organic Chemistry, and of course, he's the current chair for the Division of Organic Chemistry of the ACS. He's received a number of awards, fellowships, and honors, both nationally and internationally, including international recognition such as Senior Scientist Fellowships from both the Humboldt Foundation and the Japan Society for the Promotion of Science, and the Research Achievement Award from the International Society for Polycyclic Aromatic Hydrocarbons. He's also received the American Chemical Society George Olaw Award for Hydrocarbon Chemistry in 2011, and has been elected as a Fellow of the American Chemical Society and the American Association for the Advancement of Science. Contributing over 230 publications, his research addresses a formidable synthetic challenge of developing rational and scalable routes to isomerically pure all-carbon and carbon-rich systems. I think this research highlights a familiar theme, which is that organic synthesis is so often the key to realizing interdisciplinary scientific goals. I also realize I'm probably preaching to the converted. Today, his lecture title poses an exciting question, and I'll turn the stage over to Professor Scott to guide us toward an answer.
Thanks also to Scott for allowing me to speak at this fabulous conference. The talks have been just really spectacular, and I'm learning so much chemistry. I represent a branch of chemistry a little farther afield than some of the talks today, and we are going to talk about synthesis. So this is the bottom line. So I'm really a synthetic organic chemist, but I'm attracted to challenges in synthesis that are rather different from the ones that natural products provide or medicinal chemistry provides. And I think the spectacular successes and syntheses of complex natural products over the last several decades have really fostered a widely held belief that organic chemistry is such a mature science now that we can synthesize anything. And I think this is a myth that outsiders believe. They really think we can make anything. And I think newcomers, undergraduates, graduate students, people seeing some of the things presented here in the first couple of days could easily fall into believing that. But I think the people who have been showing you this stuff would be the first to tell you we've got a long way to go till we can synthesize just anything. When C60 was first discovered in 1985, I started thinking about this as a challenge for synthesis. And the toolbox of synthetic organic chemistry, although it's really rich and just overflowing with new reagents, new reactions, new catalysts, and more being added on a daily basis, if you look in the toolbox for organic synthesis and say, how would you make this? When we started thinking about it, it was pretty much empty. There's no way, nobody had ever thought about trying to make molecules like C60 from scratch, or from the Aldrich catalog, putting one reaction after another. How could you do this? So we'll talk about that briefly. And carbon nanotubes, which were discovered shortly after fullerenes, represent another class of challenging targets. And these are organic molecules. They were discovered by physical chemists, by physicists, astrophysicists who were not looking for these things, but they found them. But this is organic chemistry, and I think it's time that organic chemists wrestled this back to our domain and made these organic molecules. And we should be able to synthesize these things. We ought to be able to make C60 from scratch. We ought to be able to make any fullerene, C84, C88, any isomer we want, put a nitrogen in it if we want. We should be able to make any diameter carbon nanotube. So that's what we're going to talk about for the next hour. We'll start with fullerenes. We'll move on to carbon nanotubes. And if I don't get sidetracked too much along the way, we'll have a few slides at the end about some new graphene chemistry also. But the theme is going to be carbon-rich compounds. So where do you start on trying to tackle a synthesis of something like C60? And the answer is you start the same way you do with a steroid or any other target molecule. You start at the end and work backwards. You have to start breaking bonds. So what bonds do you break? There are 90 carbon-carbon bonds on C60. Every pentagon has 5 bonds, and there are 12 pentagons, so there's 60 of these bonds. And that's the one we're going to break. It's shared by a 5-membered ring and a 6-membered ring. 2/3 of the bonds on C60 are that type of bond. The others are like this, between 2 6-membered rings, the so-called 6-6 bond. And by X-ray, we know that that's a short, strong bond. That's where all the chemistry takes place on C60s. That's a very olefinic bond. This is more like the middle bond of butadiene. So if we're going to break a bond, let's break that one. And then we thought, that will allow you to cut a hole in C60. And if you go around this ring, you can cut a bigger hole and break up one of the 6-membered rings and work backwards to a sort of basket-shaped molecule. So here's a fullerene now with a hole in it. If you put hydrogens on those dangling bonds, it'd be C60H6. And whenever you work in a retrosynthetic direction, you always have to ask yourself, if I could make this, would I be able to push it on to the final product? And I think in this case, the answer is yes, because I think just heating that up, it's a symmetry allowed 2 + 2 + 2 cycloaddition to go back to close that 6-membered ring. Losing the hydrogens is actually a known process from hydrogenated fullerenes. So I think that would be okay. But this target is still a pretty horrendous looking target. It's got a lot of strain energy, and it's still got almost all of the original bonds. But if you keep cutting bonds, you can actually sort of peel this whole thing like a banana and lay it all down into the 6-membered ring at the base, and with 3 arms coming off of it. So this is C60. This is a cartographer's view of C60. It's like a map of the world laid out flat. You have to break 15 bonds to do this. And if you put hydrogens on all the dangling bonds, it's just a big hydrocarbon now, C60H30. And all of the strain energy of C60, which is enormous, is now pretty much gone. This is a more or less strain-free molecule. And it's a big molecule, but it's no longer quite as daunting a challenge to synthesize something like this, because we know how to make naphthalene and phenanthrene and things like that. We have 150 years of aromatic chemistry at our disposal to make things like this. So the real challenge is, if you got to here, could you close it back up? And what that really boils down to is, can you take a flat polycyclic network of sp2 carbon atoms and bend them, parameterize the carbon atoms all in the same direction, and then start stitching together the arms to make something like a fullerene. And that's going to involve the introduction of a lot of strain energy. But nobody had ever done this when we started. And so we started thinking about how can you do that. And there are two parts to the challenge. If we're going to make these 15 bonds, we're presumably going to make the last ones we had to break to get here first, to go back in the back direction. So that would mean a bond, say, between this carbon atom and that carbon atom. Those two carbon atoms are really far apart. This is the length of a carbon-carbon bond, and those are more than twice that distance apart from each other. So they're not even within bonding distance. So the first challenge is, how do you even get them close enough together to make a bond? You have to be close enough within bonding distance to make the bond. And then just getting them close enough together isn't necessarily going to force them to make a bond. You have to address the reactivity, complementarity. So we thought, how can we get two carbon atoms that are so far apart together? And this is when we started thinking about, molecules really are not static. These ChemDraw makes it look like a static structure. Our molecular models are static, but in reality, bonds are stretching and compressing all the time, and bond angles are changing all the time. Molecules are in motion, just at room temperature, and one of the motions of big flat molecules like this are out-of-plane motions, where a whole arm will go up and down out of plane, above the plane, below the plane, and when one arm is up, the others are going to be going up and down. And if two arms come up at the same time, then parts of the molecule that used to be remote get closer and closer together. And in particular, this carbon and this carbon will get closer together if both of those arms come up. Now, the amplitude of these vibrations is going to be temperature dependent. The higher the temperature, the bigger the amplitude of these vibrations. So we thought maybe we can just use temperature, just heat, to bend this molecule temporarily. Periodically, these carbons are going to get within bonding distance of each other. So maybe we can use heat to bend the molecule, and that pays the price of the strain. But how are you going to make a bond between these two carbon atoms? And in this case, that's an sp2 carbon atom, and it's connected by a whole string of sp2 carbon atoms. This is really just a triene. It's a triene buried in a big polycyclic system. And if we bend these two arms up, that's really a disrotatory electrocyclic reaction of a hexatriene going to a cyclohexadiene. You could actually make a carbon-carbon bond. That's ordinarily, if you get a sigma bond at the expense of a pi bond, that's exothermic. In this case, you get a sigma bond at the expense of pi bonds, but these pi bonds are part of aromatic rings, and you're building in a lot of strain, so it's clearly going to be uphill in energy to make that bond. But, so it's reversible. But if you ever make that bond and break one of the hydrogens, because there's a hydrogen attached here and a hydrogen attached there, if you break a hydrogen instead of the CC bond, then you aromatize the ring, either this ring or this ring, and you can't then break that carbon-carbon bond so easily. And then if you lose the other hydrogen, you re-aromatize the other ring, and you've accomplished what we set out to accomplish, made a bond. So maybe just by brute force, no reagents, just heat, we could do a thermal cyclodehydrogenation to make this bond, and then another one here and another one here, and then once those things start getting closer and closer together, other things that used to be far apart get close together, and maybe just thermally we could stitch this whole thing back up and use heat to pay the price. Entropy is your friend at high temperatures. Hydrogens go away, they're never going to come back, and we can just close the whole thing up. So that was the concept. It was totally untested, so we thought maybe we should test it before we try to build this molecule. And we could test it on a smaller just the core of this molecule. If we lop off the outside naphthalines on each of these arms, there's a central core that's just 36 carbons, and it still has the opportunity for this bond and this bond and this bond. And let's take some of that and heat it up. Well, how are you going to heat up something like this? Won't it just decompose or polymerize? And there's a venerable technique from the 1800s known as flash vacuum pyrolysis. You just take a quartz tube and you can heat it up with nichrome wire or in a furnace to whatever temperature you want. Put your sample over here in a chamber, vacuum pump over here, sublime the sample, it goes through, at whatever temperature for a fraction of a second into a trap. And you can do thermal chemistry in the gas phase, and depending on the rate of sublimation, you can keep the concentration of molecules really low to prevent biomolecular chemistry. So we thought, let's try it. And it works. So here's the molecule, the core, 36 carbons. This stands for flash vacuum pyrolysis. And we put that through a flash vacuum pyrolysis tube, and it makes this bond and this bond and this bond. And we get this bowl-shaped molecule, which is now pyramidalized. It can't go back down flat again because it's got these new bonds. And this is 60% of C60. The 5 and 6-membered rings map directly onto the network of carbon atoms on C60 in one step from the Aldrich catalog. This is commercially available with no reagents. This is a reaction that could have been done 100 years ago, but there wasn't nobody thought about doing these kinds of things. The temperature, of course, is outrageous. It's incredible that anything organic survives at 1,200 degrees. And not a lot of it does survive. The yield is abysmally low. This is, when we first published this, the yield was 0.2%. And we've optimized it over a period of about more than a decade. And this is, we've never been able to get up to 1%. So, we're already below 1% yield for making only 3 bonds, and we've got to make 15 bonds. So we've got to do better than this. So we started thinking, okay, we actually, the toolbox is not empty now. We've got a tool. We can use heat to bend molecules, and we validated this. So this concept of using heat to get things close together works. We need a better way to make the bond. So what's a better way to make a bond? Well, maybe instead of just pushing 2 unfunctionalized CH groups into each other, it would be better if we had a radical here. Instead of a CH bond, what if we had an aerial radical? Aerial radicals are really reactive, and when these get close together, that could be a radical addition to the pi system. You get them, and then a delocalized radical, much more stable radical than the aerial radical. You've made the CC bond. You only have to lose 1 hydrogen to re-aromatize. That ought to be better. So how can you make a radical up there? And we thought, maybe instead of attaching a hydrogen, let's just attach another atom that has a weaker bond than all of the other bonds in the molecule. Then when it goes through the hot tube, that atom breaks off and leaves a radical, just a homolysis, leaves a radical. And that works. We chose chlorine and put a chlorine atom, 1 in each pocket. You can't just chlorinate the hydrocarbon to do this. We had to build this from scratch with the chlorine in the starting material, but it's only about 5 steps to build this. And it works. We can get away with lower temperatures. It's still pretty hot, but the yield goes up 50-fold. Now we've got, this is another tool for us in the toolbox. We've just doubled our number of tools. We've got, we can use heat to bend the molecules, and as long as we put a radical where we want to make the bond, now we've actually got a pretty decent reaction for making the CC bonds. And we've used this strategy to make probably several dozen now other bowl-shaped polycyclic aromatic compounds. And I'm going to show just a couple of these because they illustrate some new points. Here's one that's exactly half of C60. This is C30H12. If you take a model of C60 and cut it around the equator and take the top off, this is what the top looks like, and it's also what the bottom looks like. You get 2 of these C30H12 molecules. So you could imagine making C60 synthetically by stitching 2 of these together, maybe putting something inside before you stitch it together. We synthesized this by flash vacuum pyrolysis of this tribromide, and in this case, we were able to make the halide directly by halogenation of the hydrocarbon. So this was a known hydrocarbon. We actually developed a quicker synthesis of the hydrocarbon. And direct bromination puts the bromines exactly where we expected. This is phenanthrene. There's 3 arms here. They're all the same. They all look like phenanthrene. And the middle bond of phenanthrene, or the middle ring, is the reactive part of phenanthrene. So we expected the bromination to take place here. And the bromine could go either there or there. This site is more hindered. There's a hydrogen here and there's a hydrogen there. They're right in each other's face. And putting a bromine in that pocket is actually not so easy. So the bromine chooses to go to the less hindered end. And then once there's 1 bromine on there, the second one doesn't go there, it goes to the other rings, and this stops after 3 bromines in high yield. Now, that's going to put the radical in the wrong place, but we decided we would make this and pyrolyze it anyway, because when the bromine comes off and there's a radical there, no matter how much you bend this thing, that radical is not going to be able to reach one of the other arms. It really can't, there's no cyclization possible. And the only thing we could think of that this radical could do would be to shift the hydrogen that's attached here, that's in this strained cove region. Once the bromine's gone, there's an open valence, that hydrogen can do a 1-2 shift over and take the place of where the bromine is. That would then relieve the strain energy. We calculate between 5 and 10 kilocalories per mole relief of strain energy for that hydrogen shift. And it puts the radical right where we want it. Now it can cyclize to make that 5-membered ring. And we don't know the exact order of events, but when we put this through the flash vacuum pyrolysis tube, this is what it makes. And we get about a 10% yield of this overall, but there's a lot going on here. This 1-2 shift of hydrogen radicals, or hydrogen atoms in aerial radicals, was an unknown process when we did this, so we were gambling that this would work. The calculated barrier is around 60 kilocalories per mole, so this is not a process that has ever been seen in solution. But we're working under conditions where we can break bonds that are 80 kilocalories per mole, so we thought this ought to work, and it does. And we can put a gram of this through the flash vacuum pyrolysis tube in an afternoon. I've had undergraduates make hundreds of milligrams of this, and we use it as a starting material for other projects. Here's the last practice compound, I'm going to call these now. We were trying to make 5-membered rings by closing here, and this works. We get all 4 of the new 5-membered rings, but we got a surprise. We actually got 2 extra bonds. This bond over here we weren't counting on, and this bond over here we weren't counting on. So we've got 6 new bonds with only 4 radical precursors. So the heat does bend the molecule, and the radicals do close up the rings. But once there seems to be a cascade process, once the curvature starts, then remote parts of the molecule that are now forced together will form bonds and spit out 2 hydrogens, this thermal cyclodehydrogenation that is not a good way to start to go from flat to bend. Once it starts bending, then it becomes a good process. And this cascade just closes up. If there's any more 5 or 6-membered rings that can close, they will. And then once you get to this stage, there are no more. Any other ring that you close would be a 4-membered ring, and we never see that sort of thing close up. So this is another tool, and this actually makes life a lot easier for us, because now if we want to go back to C60, we don't have to put in 16 or 15 chlorines to make these 15 bonds. Maybe we can just put in the first 3 chlorines, and that'll start the curvature, and then we just cross our fingers and hope the cascade process that works here will take us all the way to the end. So that's all you need to make C60 is these few reactions. So here's how we made it. So we did make this hydrocarbon, and we built this by, this is an acid-catalyzed aldol trimerization reaction, where the alpha position of this carbonyl reacts with the carbonyl of the next one. You lose water, and the same thing again, you lose 3 waters. This is an 1890s reaction, not of this compound, but of simpler ketones, to make triply fused benzene rings. And this is a head-to-tail trimerization, and that ensures that the sickle shape of each of these arms all go in the same direction, which is necessary to map onto C60. Now, as I just tried to convince you in the last few minutes, if we want to make a bond between here and here, the hydrocarbon is not the right precursor. We really need to put a halogen in the pocket, in each of these pockets, if we want to make those first 3 bonds. So the target molecule we chose was this one, to put the chlorine on this side. And that means our starting material should have a chlorine here. We could have put it in principle over here, and then it would have been there. But this was easier to synthesize. It's a 10-step synthesis to build this ketone. The chlorine had to come in from the starting material. It came from a chlorobenzene derivative, and then we build all these rings. And I'll show you one synthesis in a minute. And we ran the aldol trimerization reaction. And we expected, because this chlorine is bigger than a hydrogen atom, and this is now more crowded than the hydrocarbon, that the yield probably wouldn't be 85%. And in fact, it wasn't 85%. In fact, it was too low to be useful at all. It dropped not down, we thought maybe 50, 25. It dropped down to less than 5% yield. And we could just never dig this out. It's really insoluble, these big, flat molecules. are totally insoluble, not chromatographable. We could never get enough of this really to use for the flash vacuum pyrolysis. So Meg Borum, the student who was working on this, came in one day and she said, look, this chlorine is the real problem. That's what's causing our low yield, because we know when there's hydrogen there, this reaction really works well. The hydrocarbon is fine. But we have to have a chlorine, we have to have a radical to make this cyclization work. But we already know that you don't have to make the radical there. You can make the radical over here. So let's put the chlorine atom over there, which means start with the chlorine down here instead of there. And that meant she had to go back to the very beginning. So as many of you know, research is almost always 2 steps forward, 1 step back. 2 steps forward, 1 step back. So she went back to the beginning, repeated the synthesis, another 10 steps, made this ketone, ran the trimerization, and now it works just as well as the parent hydrocarbon. And that precursor is the one we put through the flash vacuum pyrolysis tube, and that works. That closes up and it makes C60. It loses chlorine, hydrogen shift. We don't know the order of the events, but it makes C60, and we can actually isolate the C60 by HPLC. Here's a picture of the HPLC trace. We have, as we share with natural product chemists, the blessing of having an authentic sample of the final target that we're trying to make. C60 was a known compound when we were trying to make it. We had an authentic sample. We knew that it had a retention time of 4.64 minutes, and that's exactly where we saw the bump. As you can see, the yield is not all that great. The area here is about 4% of the total area, and the material balance in the pyrolysis is about 25%, so now we're down in the sort of 1% range. But the UV spectrum of this, we have a diode array detector on the HPLC. The UV spectrum is identical to that of C60. We can actually run this and start collecting it in about 4 minutes and collect everything that comes out after that. We've never looked to see what these are, but presumably it's a mixture of partially cyclized materials. We collect everything here, strip it down, put it in a bottle, take the mass spectrum of it, and it is synthetic C60. There's a molecular ion, C13 isotope peaks, no other higher fullerenes. So this molecule is not just blowing apart to little pieces that come back together again, like when you vaporize graphite and make C60 the way it was first made. It's a size-specific synthesis. You only get the 60 carbon fullerene from this. And we were very careful to use a gentle ionization method for the mass spectrum. This is not a MALDI laser that might be causing the cyclization to begin with. We put an electron in. C60 is really easily reduced. Zinc will put 1 electron into the low-lying LUMO of C60 and make a stable radical anion. Just put a syringe in there, squirt it directly into an electrospray, a mass spectrometer in the negative ion mode, and this is what we see. We published this more than 10 years ago now, so that's why I wanted to brace through this first part pretty quickly. But it lays the groundwork for what I'm going to talk about next. And in principle, this should work to make any fullerene. So if you wanted to make C100, you can build a model of C100, start breaking bonds and carving it and peel it like a banana and get some big 100 carbon starting material. Go to the lab, synthesize it, put some radical precursors at appropriate places, pyrolyze it, and then it ought to close up to make that isomer of C100. We haven't actually done that, but I'm happy to say that others have taken this up. I wanted to show you the synthesis of, this is how we actually make this precursor. And this is really simple chemistry. There's the starting material. That's not actually commercially available, but it's an easy sophomore organic chemistry synthesis problem. Wittig reaction with this aldehyde to make this alkene, mixture of cis and trans isomers. Photocyclization, the isomers interconvert with each other, close up this bond. This is a reaction discovered in Jack Roberts' lab back in the 1950s by Frank Mallory, working with Jack, to make this cyclization, to make this 4-helicine, and then NBS bromination of that methyl group, SN2 reaction. I mean, nothing could be simpler. There's no reaction on here that's less than 50 years old. This is ancient chemistry. This could have all been done in 1950 before the first steroid was ever synthesized. Hydrolyze, acid chloride intramolecular Friedel-Crafts reaction, and I showed you this. So we can make this in 11 steps, and the pyrolysis is 12-step synthesis of C60. Others, here's a group in Stuttgart who have taken our method and applied it to higher fullerenes. So here's an isomer of C84. They did exactly what I described. You cut bonds and you peel it back down, you get this. Our 60 carbon core is in there. This has just got a couple more rings on the end of each arm, and they can cyclize it by flash vacuum pyrolysis. They didn't put any halogens in, so their yield is really small, but they can show that they get only C84, no C70, no C60 by this. And they've taken this a step further and done this not in the gas phase, but in the condensed phase by depositing this same precursor on a platinum surface and then annealing the platinum surface under ultra-high vacuum. And this gives them the surface catalyzed cyclodehydrogenation. The platinum actually catalyzes the loss of hydrogen in the formation of the bonds, and this whole thing stitches up to C84, which then opens the door, I think, to making even higher fullerenes where volatility and getting into the gas phase could be a problem. So hopefully this will be eventually scalable to other size fullerenes. But every time I tried to sell this project to one of my other graduate students, they said, well, why do you want to make C84 or C88? What's it going to be good for? We should be making carbon nanotubes, because carbon nanotubes are going to have a bigger future in nanotechnology. And we already know how to make bent sp2 networks of carbon atoms. We should be thinking about carbon nanotubes. And eventually they convinced me that, yes, I think we really should think about trying to make carbon nanotubes. So here, we're looking down the throat of a 5-5 nanotube. There's a 5-membered ring on the axis surrounded by 6-membered rings. And then the next layer is alternately 5 and 6-membered rings, and then everything else is all 6-membered rings. And one of the dreams in nanotechnology has been to use carbon nanotubes as nanowires. So if you had a molecule that could behave like a component of electronic circuits, as a diode or transistor or a memory bit or something like this, and you could connect it with a nanowire to another component, and then that to another component. In principle, you could build an entire electronic circuit out of single molecules connected by nanowires. And if you could do this, because molecules are so small and nanotubes are so small, you could shrink circuitry from what is now done by lithography on a silicon chip by another 2 orders of magnitude, maybe even 3 orders of magnitude if you go into 3 dimensions. That means your desktop computer would be small enough to fit in your wristwatch, and it would be more powerful. So this is one of the dreams of nanotechnology. Here's a carbon nanotube shown against state-of-the-art lithography, state-of-the-art actually about 10 years ago, on a silicon chip. And so this would be a ground, from the ground up building of circuitry instead of top-down by lithography. A complete paradigm shift. This hasn't been done yet, and one of the reasons it hasn't been done is that carbon nanotubes come in many different flavors. They are not all identical. They are all 6-membered rings along the shaft, so you're going to get a short course in nanotubes, because I'm pretty sure not everybody in this audience reads the nanotube literature. But they're all 6-membered rings along the shaft, and the 6-membered rings can be oriented a bunch of different ways. They can either be oriented with the pointed side up, and if it's open, then that's a so-called zigzag edge. We would call this, this is the physicist's name because they got there first. We would call this naphthalene, anthracene, a polyacene rim around the top. If the benzene rings are twisted 90 degrees so that there's a flat side up, then there's a Bay region and a benzene ring and a Bay region and a benzene ring. This looks like phenanthrene or a phenacene rim. Those are the so-called armchair nanotubes. And then anything between 0 and 90 degrees gives you these helical arrangements of 6-membered rings along the shaft. And these are chiral. This is achiral, this is achiral. These are chiral. They can be right-handed helix or left-handed helix. They can be steep pitch or gentle pitch. And whenever nanotubes are made, you get a mixture of all of these. So vaporization of carbon or chemical vapor deposition or any of the known ways of making carbon nanotubes always makes mixtures of these. And you get all different diameters of these, and you get double wall tubes and multi-wall tubes. It's random. Nobody really knows how the nucleation starts or what starts to grow the nanotube. Once the nanotube starts growing, if it starts out as a zigzag tube, you get a zigzag tube, and the next one over might be an armchair tube. And that wouldn't be a problem for some applications, but for electronics applications, it is a problem because most of the chiral tubes are not metallic in their behavior. Some are, depending on the pitch of the helix and the diameter of the tube, but most are semiconductors, and the same is true for the zigzag tubes. But the armchair tubes are all metallic. These are the ones that can be nanowires. Regardless of the diameter. This one has 5 benzene rings around the top, but if it had 6 or 8 or 10 or 20, all of these are metallic in their behavior. That is, you can conduct electricity from one end to the other essentially with no resistance. These are the ones you want as nanowires. So there's 2 ways to get a pure bottle of these. One would be to take these mixtures and separate the mixtures. But you can't separate them. A lot of smart people have been working for 20 years to try to figure out how to separate these things. These are not small organic molecules that you can just dissolve in chromatograph or sublime. These are thousands or millions of carbon atoms. They're not soluble. You can't use any of the standard separation techniques to separate these from all of these. And what you want is a bottle of these. If you're going to build a circuit with 100 wires in it, you don't want to have 95 of these and a couple of these and a couple of these because any duds in your circuit's not going to work. You really need 100% purity of a single structure. That, to me, sounds like a challenge to synthetic organic chemistry. This is what we do. This is what synthetic organic chemists do. If you do your job right, you go from A to B, B to C, C to D, and when you get to the end, you run the last reaction. All the molecules that you put in the bottle are the same as every other molecule, and the job's done. So let's build these things from the ground up. And we can use, so C60 for us is actually, it turns out, a practice compound for making carbon nanotubes. So we're going to use the lessons we learned in trying to solve the fullerene problem to now try to solve this problem. So here's our outline. This is that same armchair 5.5 nanotube. It's got the flat side of the benzene ring facing out. And we envision growing this longer by adding carbon atoms to it. And as each new ring is formed, the orientation of that ring will be dictated by the orientation of the earlier carbons that are already there from the previous ring. So every ring is going to be in the same orientation. So this thing will be this will be an armchair nanotube for as long as you want to grow it. And we envision growing this from a shorter one, and the shortest you could actually make would be just this end cap. So this has an armchair rim. It has 5 benzene rings around the top, 5 Bay regions. Getting some feedback. Phone? I do. It's off. Thank you. I didn't know that. So 5 benzene rings, 5 Bay regions. What we need is a reaction that will put a 2-carbon bridge across the Bay region to build a new benzene ring out of a Bay region. And it has to happen with a single reagent that we can just throw at this molecule. The reagent will go and just do that, make a benzene ring. And we can walk away without any intervention. And if we have a reagent that'll do that, it'll see that there's 5 Bay regions here, and it'll put a benzene ring where every one of those is. But every time you put 2 new benzene rings next to each other, you make a new Bay region, and you never run out of Bay regions. So there's always Bay regions. So this is a polymerization. It's a 2-carbon. You need a 2-carbon monomer that will add, instead of making a linear chain of carbon atoms, you're making a linear tube of carbon atoms. So it's not like the kinds of polymerizations we're used to, but it is a polymerization. And carbon nanotubes have been made and isolated and identified that are more than 1 centimeter long, actually more than 50 centimeters long, single nanotube. This is about 1 nanometer. If we could grow a 1 nanometer template like this to even 1 millimeter, that's 10 to the 6th nanometer to a millimeter. That means 1 milligram of this, in principle, translates to 1 kilogram of uniform diameter, single chirality carbon nanotubes. And I don't need a kilogram to declare victory. And we should be able to make a milligram of this. So how are we going to make this? Well, we envision making this using the technology I just showed you. If we could make something like this, this is a 50-carbon hydrocarbon. It's actually 80% of C60. If you could get this in principle starting from C60, if you could cut the top 10 carbons off and just put hydrogens on the rim. And people have been trying to do that for a long time, but nobody's succeeded in making this that way. But from the ground up, we envision making it by stitching together the arms of something like this. And this we envision making by a benzanulation, putting a benzene ring to bridge across the notch region, each of the 5 notch regions of this bowl-shaped carannulene molecule, which we have gram quantities of. So there's sort of 3 stages, annulation, and then stitch together, and then grow. And there are different challenges associated with each of these. Let's talk about this one first, because when we started this, there was no way to do this, no way to take a Bay region, turn it into a benzene ring in one step. You don't want to have to add the 2 carbons and then work up the reaction and then do something else and then come back, because you'll never make a million carbons, 2 carbons at a time that way. So imagine yourself standing on this 5-membered ring at the base, looking out over the edge, and what you see is this picket fence of Bay regions and benzene rings. And the reaction we need is one that will make a new 6-membered ring wherever it sees a Bay region, and leave 2 hydrogens on the new benzene ring. And there's another Bay region, so another 2 carbons come in, and the next one can come in either at the new Bay region or at the old Bay regions, but it can't just keep going up here. There's no Bay region. We need a reaction that'll do this, and as long as it sees Bay regions, it'll just keep making new benzene rings. And this picture looks like the beginning picture, except it's taller, and if it just kept going, it would go off the top, and the tube would just go, and you never run out of Bay regions. So this is a cartoon, but what is reality? Well, ChemDraw is not really reality, although many of us make the mistake of thinking of ChemDraw as reality. This is one step closer to trying to understand what the challenge is. How do you make a benzene ring with 2 hydrogens on it from a Bay region? Well, the minimum structural requirements for a Bay region are 3 benzene rings fused together in a nonlinear way, in a bent way this way. So this is a Bay region. And when I show this problem to even sophomores, if they've had a year of undergraduate organic chemistry, most of them say, how about a Diels-Alder reaction? This is how you taught us how to make 6-membered rings. And you say, okay, well, what dienophile are you going to use? You want 2 carbons and 2 hydrogens on it. You use up one of the pi bonds, so you must start with 2 pi bonds. So just start with acetylene in this Bay region, and you should be able to do a Diels-Alder reaction to make this 6-membered ring. There are some problems with this approach. There are actually 3 problems I can identify pretty quickly. One is that this isn't really the product of the Diels-Alder reaction. The real product is this. There are hydrogen atoms in this Bay region attached here and here, and those are still there after the Diels-Alder reaction. But they're going to be cis to each other because of the stereochemistry of the Diels-Alder reaction. And because they're in a 1,4 relationship with a double bond in between, they can be lost in a thermal reaction as a retro 4+2, essentially a Diels-Alder reaction going the other way, where the HH sigma bond is the 2-electron component. And there's actually precedent for that, even in the absence of oxidizing agents, thermal loss of H2 from something like this, especially given the driving force to aromatize these rings. So we're not really worried about that as a problem. The real problems are that acetylene is a really lousy dienophile, and the Bay region of polycyclic aromatic hydrocarbons is a pretty lousy diene. We're going to have to destroy the aromaticity of this benzene ring to make an sp3 center there. And this benzene ring is going to have its aromaticity destroyed. And in fact, that ring is not aromatic anymore. There are no aromatic rings here. And there are 3 rings here. Now, on a scale where benzene is considered to have an aromatic stabilization energy of, say, 36 kilocalories per mole. This, if these were hydrogens, this would be phenanthrene. Phenanthrene is more aromatic stabilization energy than benzene. It's not 3 times 36, but it's about 90 on that scale. And that 90 kilocalories per mole of cyclic conjugation aromatic stabilization is all gone. So whatever the activation energy is for the Diels-Alder reaction, you've got to add another 90 to get from here to there. So that's just not going to happen. If these are hydrogen and that's phenanthrene, nobody has ever successfully done a Diels-Alder reaction in the Bay region of phenanthrene. There are no examples. The world's best dienophiles will not do that Diels-Alder reaction, and it's because of this huge loss of aromaticity to do that. That leaves behind still the problem of acetylene being a bad dienophile, but Diels-Alder reactions in the Bay regions of hydrocarbons are actually not totally unknown. They're unknown on phenanthrene, but this is pyrroline, so it's the same as phenanthrene, still got those 3 rings, and then one more extra ring in this corner and one in this corner. And pyrroline, this is more than 50 years ago. Klar and Zonder, 2 of the pioneers in polycyclic aromatic hydrocarbon chemistry, found that they could throw pyrroline into molten maleic anhydride, and this is pretty brutal. Maleic anhydride melts just below 200 degrees, no solvent, so a really good dienophile. But you throw this in and it will do the Diels-Alder reaction. They used chloranil as an oxidizing agent to help lose these hydrogens and the hydrogens on the maleic anhydride to go all the way to the fully aromatic system. But they can isolate this product. So why does this Diels-Alder reaction work and phenanthrene doesn't work? Under these conditions, or even with better dienophiles, doesn't work. But this extra benzene ring in the corner, it looks like it's just an innocent spectator. It stays aromatic all the way through. How does it influence, how does it make the Diels-Alder reaction over here possible? And I think the answer is, and this really hasn't been addressed in the literature, but the answer is that this product still has phenanthrene in it. So there's an aromatic stabilization energy associated with these 3 rings of 90 kilocalories per mole. And the starting material, and this is now 5 rings, but it's not 5 times 36, and it's also not 180 kilocalories per mole. The aromatic stabilization energy of pyrroline is on the order of 120 kilocalories per mole. So the key is that the loss of aromaticity in destroying the aromaticity of this ring temporarily and this ring temporarily, that's 2 rings out of 5. And that's costing you now not 90 kilocalories per mole, but something more like 30 kilocalories per mole. There's a huge gain by just putting on these 2 rings on the back side that look innocent. So it got us thinking about, well, what would happen if we put more benzene rings on back here? They would stay aromatic all the way through this too, and the aromaticity of the retained portion would be a bigger and bigger number, and the loss would still just be these 2 rings. So maybe losing 2 rings out of 8 or 2 rings out of 20 would make the Diels-Alder reaction even better. So you can convince yourself just by drawing resonance structures and counting resonance structures that, in fact, this really ought to be true, but you can do better than that because modern computers can find transition states and calculate energies for transition states. So we did that at the B3 lip level of theory. We just used acetylene as the standard dienophile, and the Diels-Alder reaction in the Bay region of phenanthrene is high. It's lower for pyrroline. It's even lower for the longer ones and the longer ones. This is as far as we went. And it looks like it's leveling off here at somewhere around 20. But this starts to look like the sidewall of a carbon nanotube, an armchair carbon nanotube. So the prediction is that once the carbon nanotube starts growing, it's going to get easier and easier to do Diels-Alder chemistry if you can just get the thing started. So this is still just speculation. I mean, it's calculation, but this isn't fact because it hasn't been validated yet. What's known is this point works. The Diels-Alder reaction here works. This one fails. But what about this? So we thought, let's test this before we get into it too far. Does this do Diels-Alder chemistry in the Bay region any easier than pyrroline? And nobody had ever looked at that. This is a known compound, but it's totally insoluble. It's blue. Has a pretty small homolumo gap, actually. So we made a derivative with substituents here and here to solubilize it. We chose mesotyl groups, which prevent the packing of this into a stable crystal lattice. This is soluble, and just in toluene with an ordinary dienophile, not at 200 degrees, but ordinary Diels-Alder conditions, this works. These Bay regions react with acetylene dicarboxylic ester to make the new 6-membered ring, and those 2 hydrogens that were on there from the Bay region, those are lost spontaneously. So here, that one problem I said you shouldn't have to worry about, you don't have to worry about. This is a good example. Hydrogen's lost. There's no oxidizing agent in here. Makes this new benzene ring. Same thing happens over on the other side. You get 2 new benzene rings. We did a competition experiment between this and pyrroline. Pyrroline's totally untouched. Only these Bay regions react. That's as close as we come to doing real kinetics. It's at least 100 or 1,000 times more reactive than pyrroline. And you can make new benzene rings quite easily. So this second problem of the diene really being a lousy diene, it's not really true. It's, these dienes are not lousy dienes. It's that phenanthrine's a lousy model for the kinds of dienes that we want. If the diene is part of a polycyclic aromatic system, but it's a big enough polycyclic aromatic system so that the loss of aromaticity in making the first 2 new sigma bonds, as long as that's small enough, this is an okay reaction. That leaves one problem. The dienophile. We can't use acetylene dicarboxylic ester because we need hydrogens on there, and we can't hydrolyze and decarboxylate the way Clar and Zonder did, because we're not going to try to do this just 1 ring at a time. So we need to get from here to all hydrogens in one shot. But it doesn't have to be acetylene as the dienophile. It could be an alkene with an X group on it that makes this a good dienophile, good enough to do the Diels-Alder reaction, and then the hydrogen loss is going to work. And then if X has been chosen right, we can do an HX elimination to make a carbon-carbon double bond and leave behind those 2 hydrogens. And 30 years ago, Leo Paquette introduced a masked acetylene of this sort, where X is a phenyl sulfoxide, and that's an electron withdrawing group. Does Diels-Alder chemistry. He didn't do it in Bay regions like this, but just with ordinary dienes. And then HX loss is a sulfoxide elimination. Turns out phenyl vinyl sulfoxide is not a potent enough dienophile to do this kind of chemistry with pyrroline, for example. It just polymerizes. So we went back to the computer and started playing with, what other X groups could we put on there. And pretty quickly we came to the most powerful electron withdrawing group that we have as organic chemists. Single electron withdrawing group that's neutral is a nitro group. And nitroethylene is a really powerful dienophile. And nitroethylene does exactly this. We take this compound with nitroethylene, heat it up just in toluene, and boom, boom, it makes 2 new benzene rings with hydrogens on them, which is exactly the reaction we want. Wherever you see a Bay region, it makes a new benzene ring, presumably going by just the process I described, Diels-Alder reaction to make the 2 new sigma bonds and the new 6-membered ring. Loss of hydrogen is spontaneous. And then this last step, this loss, the HX loss, was not one that we were completely confident about, because this looks kind of like a cope elimination, where instead of a tertiary amine N oxide, it's a nitro O minus, can reach over and pull off this hydrogen in a concerted cyclic transition state. But ordinary nitro compounds just don't do this. If you take nitrocyclohexane and heat it up in hot toluene or boil it, it doesn't fall apart to cyclohexene and HNO2. But this is not an ordinary nitro compound. Because of this step, the rearomatization of this ring and this ring, that carbon-nitrogen bond is now benzylic. And the carbon-hydrogen bond is also now benzylic. That weakens this bond by quite a bit, weakens this bond by quite a bit, and both of those bonds are breaking in the transition state. So that lowers the activation energy for this HX loss, plus the new double bond that we're making is part of a new benzene ring, so there's a real driving force for this. And all of those energetic components conspire to make this, this reaction work. We don't know what the minimum temperature is for this to work, but it's a great masked acetylene for this particular application of turning Bay regions into benzene rings. So that's a big part of the battle. That's that last step of what we need to do. That's this part. So let's talk about this part. How are we going to make this? Well, we want to stitch the arms together, but the hydrocarbon, the C50H20, is probably not the right compound to use. I mean, we could put this through a flash vacuum pyrolysis tube, and maybe we would get a little bit of this, but we've got to make 5 new bonds now. This is, in fact, the same kind of arrangement, 6-membered ring, 5, 6, 5, 6, that we had before, where we were getting less than 1% yield starting from the hydrocarbon. But we could boost the yield a lot by putting a radical precursor in the pockets. So what we really want is a radical precursor in each of these pockets. And if we had the hydrocarbon, that's not where direct chlorination is going to go. So we're going to probably have to carry these chlorines through from starting materials in order to build this. So we're going to have to build this framework with the chlorines on there, which means the retrosynthetic analysis is to start breaking carbon-carbon bonds. And we would like to maintain the 5-fold symmetry of this. We don't want to make 1 ring at a time, but we'd like to make 5 bonds at a time and then 5 bonds. So where do we break this? There's a couple of choices. This is the one we chose to follow. If we break this bond and then every other bond around the rim, here, 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 that allows you to work backwards to a pentasubstituted chloraniline, where the bond we broke, we said, okay, let's put a hydrogen on this end and a chlorine on that end, and that gives us a 2,6-dichlorophenyl substituent. So this is now our target, because we think we could get from here and close that up to here, and if we could get from here to here, we could close these up. So here's what we really need to make. So how are we going to make pentasubstituted chloraniline? Well, this is an aryl-aryl bond, and there's a lot of chemistry in the toolbox from the last 10 years for making aryl-aryl bonds, including really hindered ones of this sort, just by Suzuki chemistry or Negishi chemistry. And in principle, you could make this by making a boronic acid here, which is commercially available, and a halogen there. So you need pentahalogenated chloraniline. Or the other way around, you could have, say, a bromine or an iodine there, and a boron on the chloraniline, have 5 borons on the chloraniline. And we've actually explored both of these. In fact, both can be made to work. I want to talk about the second one, putting the boron on the chloraniline here, 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 and here. Because there's a lot of recent chemistry, especially the iridium-catalyzed borylation reactions, championed by people like Hartwig and Marder, which would allow us to take chloraniline directly to the pentaborylated chloraniline, if we could somehow control the regiochemistry. The normal catalysts for that are this iridium dimer, and the reagent, when the boron reagent is B2-pin2, usually with this ligand or various other bipyridyls, at elevated temperatures in various solvents. And this is the compound we want. But we were fully aware that after the first boron goes on, there's very little effect, very little in the way of directing effects of borons for subsequent borylations. This is a CH activation process. It's not electrophilic aromatic substitution where the pi system is disrupted and you look where the cations are stabilized by substituents. This is sort of in-plane chemistry. And the only influence really of the first boron is steric. So you never get a second boron on the same ring, and you never get 2 borons peri to each other across from the notch. So if the first one goes on there, they're all the first one can't go wrong. They're all 10 positions are equivalent. If the second one goes there, that's great, and the third, fourth, fifth. So some of it's going to go this way. But if the second one goes over here, then this ring is already blocked, because you're not going to put a boron next to this boron, and you're not going to put one there next to this. So this ring is going to stay unblocked. Each of these has room to take a boron. You can get up to 4 borons, but it'll stop at this isomer of tetra. Or you could get this isomer of tetra, or this penta, but everything's going to stop when it gets to that. And if you just do the statistics, if you put the first one on, there's 9 positions left. The 2 adjacent positions are out of the running. So there's 7 positions left for the second boron. And 4 of the positions are good positions, and 3 of them are bad. So it's a little better than 50-50 for each one, but at each point there's dead ends that could take off. And the prediction is you get about 25% of this and 75% of this, and that's almost exactly what we got just running this borylation reaction under the literature conditions. But the student who was working on this, Maria Elisiva, came to me one day and said, I just ran this reaction, and all of a sudden the singlet for this is twice as big as it used to be. And she started tracking down what it was she had done differently in that reaction, and found that, and found out what it was, and then optimized this reaction, and found that by putting 10% sodium methoxide into the recipe, which is not part of the recipe, the literature recipe, and running this reaction for 4 days, she could push this essentially quantitatively to the desired pentaborylated compound. And what we think is happening is at the end of the first few hours, actually, you get this mixture, and there's no corannuline left, and it's mostly these tetrasubstituted corannuline and some of the pentasubstituted corannuline. But if you keep on going, the catalyst is still in there, and there's still excess borylating reagent. And every reaction in chemistry is reversible. Not just catalyzed, every reaction in principle is reversible. And as long as it's not too exothermic, you should be able to get back up and go back to where you came from. And the catalyst is in here. Catalyst doesn't change the thermodynamics. And we think this methoxide is now coordinating, say, with a boron and activating this for the catalyst to come back and just by microscopic reversibility go right back to putting a hydrogen on there. And once you take the boron off, now you could put it on back here. It's going to go back on because we've got excess reagent. But if it goes on there, now it's in the right position, and this position is no longer blocked, and we can put the 5th boron on. And from here, you've actually got to do 2 shifts. You've got to go from here to here, and then from here to here. But if you do this long enough, eventually with the high catalyst loading and run this for a long time, eventually just everything siphons over to here. It's all just Le Chatelier's principle. And the reversibility of these iridium-catalyzed CH activation reactions, as far as I can find in the literature, nobody has ever reported or even talked about as a possibility. But here is really clear evidence, and we've done some smaller cases that are even more clear-cut. The reversibility really is, it's not only happening, but it's very useful, and we can make the compound we want here in essentially quantitative yield. There's isolating this is, the default setting for most students is you run your reaction, work it up, put it on a column, and chromatograph it. And if you try to chromatograph these things, these are all just big grease balls on the outside. There's a little bit of this, and excess reagent. So Maria found that she can just take the whole reaction mixture and dump it into methanol. This is real old school. It just crashes out. You filter off 85% analytically pure. I couldn't believe it was really pure. We actually sent it out for elemental analysis, and it's analytically pure stuff, 85% of this penta-substituted corannuline. The remaining 15% still has some of this in it and some of these. We don't try to separate those. Just take the whole mixture and boil it up, take the filtrate, boil it up into hot propionic acid, strips all the borons off of everything, takes it all back to corannuline, and then we can recycle the corannuline. So essentially no loss of material. We can make, we can take gram quantities of this and make gram quantities of this. The Suzuki reaction works great with various catalysts. This is the one we're using right now. So there's our target molecule, and we're all ready to now stitch this thing up. How do we stitch this up? Well, in an earlier generation of this approach, we had just one chlorine on each of these benzene rings, and we were able to use palladium catalysis to do an intramolecular, or an oxidative addition into the carbon-chlorine bond, and then an intramolecular CH activation, an intramolecular aerylation to make that 5-membered ring. And then we could make all 5 of those 5-membered rings this way. We tried to make all 10 of the bonds using palladium, and we can get, by mass spec, we can see up to 7 or 8 CC bonds, but never all 10. All 10 chlorines get clipped off by the palladium. but we can never get all the way to here. But flash vacuum pyrolysis does the trick. If you break off a chlorine, they're all 10 equivalent, so it doesn't matter which one first. I'll just take that one. And then that aerial radical can cyclize onto the pi system over here. Loss of a hydrogen gives you that 5-membered ring, leaves the other chlorine in the pocket where we wanted it. And we don't know the order of events again, whether all the 5-membered rings close first and then the 6-membered rings, or in fact, not every molecule has to follow the same pathway. But we get all 10 bonds and make this C50H10 molecule. The first evidence for this came from mass spec. Here's the high-resolution mass spec we got for this 610 mass units for this C50H10. Then we eventually got enough of it to take a proton NMR spectrum. All 10 hydrogens are equivalent here. So the proton NMR looks just like the mass spec singlet. This is about 7.7. I'm not sure you can read that number. The benzene's over here. This is about a half a part per million downfield from benzene. And actually, modern calculations are pretty good for rigid systems like this and hydrocarbons with no funny atoms. You can calculate NMR spectra within a tenth of, or less than a tenth of a ppm. This comes right on the money for the calculated NMR chemical shift. At this point, the student who first made this, Ed Jackson, was at the end of his thesis. He was actually starting to write his thesis and tried feverishly to grow crystals of this because we really wanted to have crystal structure before we published it. I feel really uneasy publishing a structure proof based on just a singlet like this. Even though the mass spec, I was confident that this is it, but there's nothing as convincing as an X-ray structure. And poor Ed, he could never get the crystals to grow, and he got his thesis and he left, and a successor, Brian Steinberg, took over the project. He repeated the synthesis, made more of the compound, improved the route to some extent, and he spent most of a year trying to grow crystals, and he could not get crystals. He wrote his thesis and left. We still hadn't published this, and a new postdoc came from Beijing, who had done fullerene chemistry for the last 5 years, and he was one of these guys that carves holes into fullerenes and makes derivatives that in tiny quantities. He got crystal structures of everything he'd ever made. So Chenyan Zhang came, and he was able to grow the crystals of this, and it looks just like the calculated structure. It's a beautiful C50H10. It's got the 5 benzene rings around the rim. There's all the Bay regions, and looks just like it's supposed to look. So we did finally publish it. And the secret, it turned out, was the solvent. It was a mixed solvent system of dichloromethane and I think tetrachloroethane. But carbon disulfide was the magic ingredient in the solvent, and we found out why in the X-ray structure, because every one of these bowls had a carbon disulfide stuck into the hole, and then the whole crystal lattice was built out of these complexes. And this actually changes the shape of the molecule. Instead of having a dimple on the top, it's got this bump on the top, and that packs differently than the empty one. We've never gotten a crystal of just the empty bowl, but always with this carbon disulfide. So we finally published this just last year. So there we are. Now we've got this template, we've got the end cap, we've got this nitroethylene method for growing things. There's all these Bay regions around the edge. So as soon as we got the X-ray structure and started to have enough material to actually do chemistry, we put this in with nitroethylene and ran the reaction for however long we ran it, worked it up, and we just got starting material back without the carbon disulfide. And we ran it longer, and one of the problems is that nitroethylene, because it's so reactive, it also polymerizes, so you get polynitroethylene. So we use a big excess of nitroethylene. We generate it in situ. It makes more and more polymer, but this stuff is just inert. No reaction with nitroethylene. Why not? So we went to the computer and we calculate, and we discovered, probably should have, before we started the project, that the Diels-Alder cycloaddition on the Bay region, so that you can't, it's hard to tell here, but this is one of the Bay regions. But the p orbital here is, they come out from the central axis this way. This p orbital is coming out this way. So nitroethylene's got to span two p orbitals that are pointing away from each other. And that raises the activation energy for this transition state. There's a lot of strain to bring this whole thing together to make the transition state for the Diels-Alder reaction. And this shows up in the calculations. The 5,5 nanotube is calculated to have a really high barrier by B3 lip or AM1. But as you go to a bigger diameter tube, of course, that divergence of the p orbitals gets less and less and less. And as you go to a 6,6 tube, the barrier gets lower. And the 10,10 tube with 10 benzene rings around the top is now close enough to being flat. Looks, if you get a curvature that's a big enough diameter, like the world looks flat, these things start to look flat. And the calculated barrier is down here in the 25 to 30 range. This is the calculated barrier for the bisanthene and the pyrroline that we know work with nitroethylene. So this is another case of 2 steps forward, 1 step back. We picked the wrong size ring. And so instead of making the 5,5 nanotube end cap, we really needed to make the 6,6 or the 10,10, and we are currently working on routes to 6,6 nanotubes and 10,10 nanotubes. And I don't have time to tell you, what time did I start? AJ?
Started about 10 after.
Okay. I'm not going to tell you about how we're trying to make the 1010 nanotube, but I do have a couple more slides I want to tell you about some very recent chemistry in collaboration with Ken Itami in Japan. Itami published a paper in 2011 that caught our eye. It's a way to stick benzene rings directly onto polycyclic aromatic hydrocarbons using boronic acids, or actually these cyclic anhydrides of boronic acids. And it uses palladium-2 as the catalytic species, end up with palladium-0, which gets reoxidized with chloranil. And it's an unusual reaction of this is pyrene. Pyrene normally reacts in nitration and halogenation, things like that, up on this top ring or the bottom ring, but not on the side ring, this so-called K region of the pyrene. So it's unusual, and corannuline is all K regions. So he sent a student over to my lab, and we did this chemistry with corannuline, and we've quickly found that we can put more than 1 benzene ring on each K region. In fact, we can push it all the way to make decaphenyl corannuline. And we were really interested in decaphenyl corannuline because this is so crowded. These benzene rings they're all tilted up and crowded into each other's face. The way they can relieve the compression between them is to all pull away from the middle. That gets them further apart from each other, but it also tends to pull this bowl-shaped molecule and flatten it out. And by calculations, it's virtually a flat molecule, depending on what level of theory one uses. So we were happy to get a crystal structure of this, of the parachloro compound, and it looks just like the calculation. If you look closely in the middle here, there's a 5-membered ring a little bit above the plane, and then there's another one a little bit below the plane. So it's actually disordered in the crystal. Some of the molecules have a very shallow bowl down, and some have a very shallow bowl up. And probably in the crystal, we calculate the barrier for flattening this is only about 1.5 kilocalories per mole, so less than the barrier of rotation in ethane. And this thing is probably inverting rapidly just in the crystal. There's nothing to prevent it from this. So it's vibrating like a drum head or a trampoline. We can't prove that experimentally, but this is what it looks like in the X-ray structure. The other part of the attraction of this was that we could stitch this up. All the ortho positions can be coupled together under these oxidative cyclization conditions in pretty good yield for the para-T-butyl system. And this makes a big graphene-type molecule with 26 fully unsaturated rings. They are not all 6-membered rings, so there's a 5-membered ring in the middle. And when you stitch these together, the ortho ones make a 6-membered ring, but if they're paired to each other, that's a 7-membered ring. So there's alternately 6 and 7-membered rings. These 7-membered rings give you a sort of saddle-shaped negative curvature. So this thing is grossly distorted away from planarity, and because of that, it's soluble in common organic solvents, and we can make it by direct CH activation using the Itami method to put 5 biphenyleals on and stitch it up, or we can take our pentaborylated thing and with Suzuki put 5 of them on to get a single isomer and stitch it up. So we can make this 2 or 3 different ways. And we got an X-ray structure that looks like this grossly warped graphene. And the grossly warped graphene is has a bunch of properties I'm not going to go through. It has a larger HOMO-LUMO gap than the all hexagonal 6 system. And I think this is a hint to the sorts of things that synthetic organics chemists will be able to do in graphene chemistry. By the selective introduction of odd-membered rings, you can change the planarity and tune the optical properties and tune the electronic properties. We just sent the galleys back to Nature Chemistry. This will be coming out in the next week or so. So what's the answer? Can organic chemists deliver structurally uniform fullerenes and carbon nanotubes by custom synthesis? And I think the answer is today, if a physical chemist comes up and says to us, can you make C88? The answer is probably no, I don't think we can deliver it yet. But we can make a smidgen. Tomorrow, these are solvable problems. So I think the answer to this is yes. Tomorrow we are going to be able to make these things. Maybe not tomorrow, the day after tomorrow. And it may not be me, but it may be all of you students out here. I hope some of you will move toward this direction. It's not only natural products that create challenges for synthesis, but material science has things that only organic chemists are going to solve. And in fact, we have an obligation, I think, as organic chemists to try to make good on this. We ought to be able to make anything. We can't make anything yet, but we ought to be able to make any of these things. The students who worked on this obviously span quite a number of years. I don't have a single picture with all of them in it. These are some of the more recent ones. Eric Fort did all of the nitroethylene Diels-Alder chemistry I talked about. He's now an assistant professor at St. Thomas College, his alma mater actually back in Minnesota. Brian Steinberg did some of the improvements on the C50H10 synthesis. Tony Belanger and Allison Green are both working on 6,6 nanotube syntheses, and Jen Quimby is working on a 1010 nanotube synthesis. The rest of these, Natalie Smith's working on pentabenzocaranulene, which I didn't talk about. The rest of these are undergraduates. 3 of them have gone off to medical school. Jacob Ishibashi is a third-year graduate student at the University of Oregon with Professor Liu, but he's coming back to BC in a month because Professor Liu is going to move to Boston College. With that, I'd like to thank the National Science Foundation. Can't do this without money. I may be the only speaker that doesn't have an NIH acknowledgement, but very thankful to the NSF, and that's all. Thank you.
Sorry. We have time for a few questions. I had a question, actually. Oh, is there one here? Thank you.
Oh, somebody else had a question?
Go ahead.
Hi, Kerry Fowler from Canetta in Seattle. First of all, I can't wait to go back to work and tell my biologists that I saw someone make something more soluble by putting acetylene on it. That's a medicinal chemistry joke, I guess. I was, last night, the winning poster that we saw last night was Anna Wagner's, I think it was, and she was making carbon-carbon bonds just from naphthalene and a benzene ring with platinum salts. And in the early days when you were trying to get these CH carbons to link up, did you try any metal catalyzed reactions? Because I didn't see metals show up very often in your work.
Yeah, so we have, but because we're putting so much strain energy in here, these things just don't go in solution phase under ordinary 100 degrees or even 200 degrees. So I think we really need to have the kinds of temperatures that we're getting in the flash vacuum pyrolysis. We have actually put metals in the flash vacuum pyrolysis tube to see if we can catalyze them on the way by, but we've never had very much success doing it that way. This group in Stuttgart who've just started doing surface catalyzed cyclodehydrogenations, so they make the big planar starting materials, and they put them down on a platinum surface, and then annealing those makes carbon-carbon bonds between two just CH positions. So I think that's a direction that may develop. Yeah.
So Larry, in terms of the reorganization of the B pins about the molecule,
Yeah.
do you think it's the iridium hydride species that's just coming back? Because typically speaking, when we think about those mechanisms, it's either HB pin that's being produced from the reaction with B2 pin 2, or then hydrogen gas when that HB pin comes back. And I would think that the hydrogen gas is going to be lost under your system and not be able to come back. And so do you think it's the iridium hydride that's coming back, or is it re-engaging HB pin? And can you tell by perhaps following the reaction by boron NMR whether or not you are actually doing that?
So the first answer is I don't know. The second is a comment that these are done in a sealed tube, so the hydrogen gas actually wouldn't get away. It would be mostly in the headspace, but some will be dissolved. So it's conceivable actually that hydrogen gas could be involved, and the HB pin certainly is going to be in there still if there's any left. And the hydrogen in B2 pin 2 could go back to HB pin. So I don't know the answer, but everything that was in there to catalyze the reaction in the forward direction is still in the flask.
I guess just to follow up, so then do you know, is the HB pin being consumed? Because I think you have twice as much B2 pin 2 as you need to get them all on there.
Right.
And often that's slower borylating species itself. And do you know if it's reacting at all?
We don't know. So we've got 5 CH positions that we're putting boron on, and we use a little more than 5 equivalents of B2 pin 2. So we've got actually 10 borons for the 5 positions. Yeah, you're right. You get BH pin as one of the byproducts of the borylation, but you can do these borylations just starting with HB pin. It's not as active as B2 pin 2 though.
Please join me in thanking Professor Scott once again.